So good evening everyone. Yeah. So we'll start classification of elements and periodicity in the properties of those elements. Okay. So first of all, why do we need to classify elements? This will be the general question. So at early days, what we know, very few elements were known right now. So those elements at that time, it is not very difficult to remember because there are very few elements known. But later on, as discovery goes on, we got new elements added up into the list. Now it is becoming difficult to remember all these things. Okay. So now the scientists later they thought of classifying these elements based on their different approaches. Okay. Some scientists classified based on their properties, like their reactivity, something like this, based on their mass numbers, something like that. Different scientists have their different approaches. Okay. So that is what are the what are the periodic tables we have seen? Daubernier triads, other next Newland's law of octave. So something like this, we have different classifications. Okay, like arrangement of elements right now. So now, like what I can say, periodic table means it is a arrangement of atoms based on their properties. Okay, given by different scientists based on their own approaches. Okay, so finally we are following now the Moseley's periodic table. Okay, yeah. So it is something like if you go to a library and there will be different set of books right now. So if they are randomly arranged, it is very difficult to take the book that we required or we are looking for. But if they are arranged based on their subject or based on their sector, something like that. Okay, now we can go to the subject that we are looking for and we can pick our book from there right now. So that is easy. Similar to that, the elements were also classified here. Okay, just to make us easy. Okay, while studying their properties or looking their reactivity and all. Okay, so now, so what is the first development for this periodic table? So it is Daubernier's triad. So this person, the Daubernier triad, he classified the elements based on the arrangement of their atomic mass. So increasing he has taken set of three elements he taken. So he arranged these three elements based on their increasing atomic weights. Okay. Now what he observed is the mass, for example A, B, C are the three elements arranged based on their increasing atomic weight. The mass of the middle element, atomic weight of middle element will be average of the first and third element. So what he told that atomic weight of B is average of atomic weights of A and atomic weight of C by 2. Okay, this is something like average of first and third element will be equals to the second element. Okay, this is the simplest way. So now let us see few examples of this. See, he taken lithium, sodium, potassium. Okay, so see lithium, sodium, potassium, if we see, these belongs to like how they are arranged based on their increasing atomic weights. See, increasing atomic weights. Now if you look at the atomic weight of this middle element, sodium, will be what? Average of atomic weights of lithium plus potassium right now. So 29 plus 39 plus 7 by 2, like that. Okay, yeah. Similar to that, if you take calcium, strontium, barium, now atomic weight of strontium will be average of atomic weights of calcium and barium. Okay, so this the first and third elements average will be equals to the second element. That is what his classification. Now they will ask you by giving 4 options, identify Daubernier triads, or which are the following is not a Daubernier triad from the following. Okay, so you need to remember this set of elements. Okay, now whatever the NCERT is given, just stick to that book. Okay, that is your standard here for this inorganic chemistry especially. Okay, so try to read every line of NCERT when it comes to inorganic chemistry. Okay, you can see the questions directly taking out from the lines of NCERT one. Okay, yeah. So there are some drawbacks or limitations for his triads. So what is that? So he was unable to arrange all the elements which were known at that time based on these triads. See, he given the set of triads only for few elements, not for all the elements known at that time. It means he was unable to explain why it is not applicable for all the elements, why it is only applicable to some elements. Okay, so hence it got failed because not applicable for the all the known elements at that time. Okay, next classification is by Newton's law of octave. See, octave means 8 elements you can take. Okay, so every first element and 8th element are having similarities in their properties. Okay, so again these elements were also arranged based on their increasing atomic weight. Okay, for example, see lithium, beryllium, like this if you observe, see lithium and sodium, like green color here you are observing now here. So they are having similar properties. See 1, 2, 3, 4, 5, 6, 7 and 8th element. First element and the 8th element are having similarities in their properties. Okay, so like that beryllium and magnesium, boron and aluminum, carbon, silicon, like that. Okay, so now how they arrange? Increasing order of atomic weights first, then first element and 8th elements are having similarities in their properties. Okay, yeah, so you can read this. And now one more thing, when he proposed this Newton's law of octave, noble gases were not discovered. Okay, therefore we got first element and 8th element similarities. Now we have noble gases. Now if we insert noble gas, now similarities will be observed for every first element and the 9th element, because see here, are you able to see any noble gas here? No, but now we have noble gases. So after like fluorine we can have neon, so it becomes now first element and the 9th element. Okay, so remember this point also. Next, now his like arrangement, this octave arrangement also applicable for only lighter elements. See here, this rule is valid only up to calcium and fails in the case of heavier elements. So it means this is also having limitation now, which is applicable only for lighter elements, not for the heavier. Okay, so when noble gases were not discovered at that time, later it is added and it is becoming 1 and 9th element. Okay, then next other further developments were also shown here. Next one is what? Lothermer classification or Lothermer curve. So what he told is, he taken a graph for atomic volume versus atomic mass of elements, and he drawn this curve. He observed these curves which were appearing when he taken atomic volume versus atomic mass. Now those elements having similar properties were occupying same position in these curves. It means, for example, see, just read this, the elements in the form of a curve between atomic volume and atomic masses stated that properties of elements are the periodic functions of their atomic volumes. See, for example, if you observe, all the alkali metals were appear to be at the peak of these curves. See, sodium here, potassium here, rubidium here. What are these elements? Alkali metals, na? They have similar properties, occupying peaks of the curve. Okay, and next, if you observe halogens, fluorine here, again chlorine here, bromine here. So what you are observing, the halogens are occupying the increasing order of the curve. Like, see, this is the increasing order, no? Increasing order of the curve, just backside of alkali metals. Okay, and before like after the halogens, what is the element present here? Noble gases. In all of these series of elements, series of these peaks, you see after halogens you have noble gas. Here also you have noble gas, here also you have noble gas. Like this we need to remember. See, remembering the points of the peaks or the curve, very very difficult, na? Like what is the positions of halogens, all the time you need to remember, or what is the position of alkali metals. Okay, so remembering for all the elements it is very difficult. Therefore this is also got failed or not approved later. Okay, first it is considered, but later it got further developments. So what are the points here you need to remember? During the exam you can see this kind of questions. See, what is the position of alkali metals in the curve? Okay, so in the Lothermer curve, what you can say? Alkali metals such as sodium, potassium, rubidium, which have similar properties, occupies peaks of the curve. Next, halogens like fluorine, chlorine, bromine, which have similar properties, occurs at the rising, increasing, or rising, or the ascending part of the curve. This terminology also you should remember. See, this kind of rising means you should not get confused, or ascending means a small to big na. So ascending, like this is on ascending na, yeah. So ascending part of the curve. Okay. Next, noble gases such as neon, argon, krypton, which have similar properties, are just before alkali metal, or just after halogens, or just before, just after halogens, or just before alkali metals, like that, or in between halogens and alkali metals. You can remember these terms. Okay. Next, hydrogen and helium to be seems to be exception to this rule, because if you see noble gases, all these noble gases are having the position between alkali metal and halogens, but helium is somewhere here, which is at the top. That is an exception, he is saying. Okay. Similarly, hydrogen also. Next classification is Mendeleev's classification. So yeah, just give me a minute. So what he is saying, see, Mendeleev arranged the elements in the horizontal rows and vertical columns of a table, okay, in the order of their increasing atomic weights. Okay, atomic weights here. The physical and chemical properties of elements are periodic functions of their atomic mass. Okay, so this is the primary condition, atomic mass he has considered. Okay, so he arranged how elements in the rows and columns. Okay, rows are called periods, like these vertical lines are called columns, that vertical columns are called groups here. Okay, so now we got two terms now, periods and groups. Okay, yeah. So characteristics of Mendeleev periodic table. What is this? It is based on atomic weight. Okay, increasing order of their atomic weights. Okay, so now 63 elements were known at that time, and noble gases were not discovered. Okay, so he was the first scientist to classify elements in the rows systematic manner, like horizontal rows and vertical columns, like periods and groups. Okay, next, horizontal rows are called periods and vertical columns are called groups. Okay, periods and groups here. Next, okay, so each group is subdivided into A and B. For example, I have first group 1, so he subdivided this as 1A, 1B. Similarly, second group as 2A, 2B, like that. Okay, so each group up to 7th is subdivided into A, B. Okay, subgroups we have now, subgroup A, subgroup B. Okay, up to 7. Okay, then next, now subgroups and called, see here, now this 8th group consists of 9 elements in rows. So it means if you look at the periodic table, at that time I will show you. Okay, the elements belong to the same group exhibit similar properties. Now if you observe the periodic table now itself, I just wanted to show you. Okay, let's discuss, and we'll discuss this thing in the periodic table. Okay, now look at here, what are the merits and advantages and disadvantages. He given some gaps in the periodic table. In his periodic table, he provided some space for unknown elements also. For example, here for gallium, he has provided the space by naming it as Ica aluminium. Okay, then later on the discovery of gallium took place, and that will be placed in the Ica aluminium, that gap provided. Okay, so what is the main advantages? He provided the space in his periodic table for unknown elements which were discovered later and perfectly fitting into that empty space provided. Okay, now remember these names. Gallium can be called as Ica aluminium. Next, scandium, Ica boron. Germanium, technetium, manganese, Ica manganese. Okay, yeah. And now what are the demerits? See, the position of hydrogen were not satisfied because it is having similarities with alkali metals and halogens. Okay, next position of isotopes. What do we mean by isotope?
Same atomic number, different mass.
So different mass numbers are there now. For example, carbon 12, carbon 13, carbon 14. These are the different isotopes of carbon. Now they differ in mass number now. It means Mendeleev given classification based on mass numbers. See, these mass numbers are differ. It means they should be arranged with different positions in his table. But he provided only one space for complete carbon atoms. Okay, so which was not explained again. Okay, so then next, anomalous pairs of elements. So again in his table there were some elements which are arranged like in contradict to his classification. He given based on what? Increasing atomic mass right now. But there are some elements, something like argon and potassium if you see. So now potassium is having smaller mass number than the argon. It means potassium should come first, then next argon. But in his table it is argon came first, potassium next. It means what he made, the bigger atomic number is arranged first, then the smaller one, which is contradicting to his classification. Okay, this is also a demerit we can say. Next something like that we have cobalt, okay, nickel and cobalt. Okay, see nickel and cobalt like this, you need to remember this anomalous pairs also. They will ask which are the following are the anomalous pairs of Mendeleev classification. Argon, potassium, cobalt, nickel. Okay, next. So then next we have modern periodic table here, that is given by Henry Moseley. So how he given this? So he has taken the elements, like X-ray spectra of the elements. Okay, so during this he used some frequency, right? Okay, so he plotted a plot of frequency of X-rays emitted against its atomic number. That gives a line, that gives a straight line. Okay, so that gives a straight line for what? Frequency versus its atomic number. How this atomic number got for him? He considered this from number of protons. Okay, so now he classified he proposed a new periodic law saying that the modern periodic law is what? The physical and chemical properties of elements are periodic functions of their atomic numbers. Okay, so now this is the most best one out of the things that we have studied till now. Okay, yeah. So what is the characteristics here? We have 18 vertical columns called groups like this. How many we have now? 18 vertical columns called groups, and 1 to 8th group and 0. Okay, so that is what? 0 group is for inert gases. Okay, inert gases were introduced in the periodic table by Ramsay. Okay, so 7 horizontal rows called period. So this is in the new periodic table here. Okay, so what are the merits of his most like Henry's position of isotopes, because now isotopes has same atomic number now. Yeah, so therefore this demerit of Mendeleev is cleared here by taking atomic number but not the mass number. Okay, so now next lanthanides and actinides in the third group. So all lanthanides, actinides present in which group? Third group. Okay, and next there is no limit like anomalous pair now. Previously we have anomalous behavior, anomalous pair, but there is no thing to study now about the anomalous pairs, because now they are purely based on their atomic number, not on the mass number. Next. So in his table, in modern periodic table, diagonal line separates out metals, metalloids, non-metals. So if you look at the p block elements, you will get a series of elements like this, which separates metals, non-metals. In between that we have metalloids. Okay, yeah. Again, when it comes to electronic configuration, elements belongs to the vertical column, that is group, have same general electronic configuration. For example, NS1 for first group, and for second group NS2, and for third group NS 2 NP1 for 13th group elements. Okay, 14th group.
NS2 NP.
So for all these p block elements you have NS2, this is fixed, NP1 to 6, like this. General electronic configuration will be fixed. Okay, so now what are the demerits? Position of hydrogen is not satisfied here also, because it is showing similarities in the properties with halogens as well as alkali metals. Okay, still it is controversial only. Okay, that's why in your standard periodic table, if you observe, that will be positioned at the top, not in the first group, not in the 17th group. Okay, helium is a inert gas but has different electronic configuration. What is the electronic configuration? You are just writing it as 2s2, but 1s2, whereas other elements will be having NS2 NP6, but except helium, all noble gases will be having that. That is also a small drawback here. Next, lanthanides and actinides are still not placed in the main frame. Okay, so isotopes have different physical properties but has that, yeah. Next, so this is about the modern periodic table. So this is what? Alkali metal, alkaline earth metals, and here we have p block elements. Okay, this is d block and the bottom of the table is f block. These are called lanthanides and this line is called actinides. See, a set of elements which are separating metals, metals and non-metals right now. So we can say them as metalloids here. So these are, there are 4 blocks in the periodic table. Okay, what are the blocks? S, P, D, F. So these first 2 groups are S and these 13th to 18th are D. Okay, this 13th to 18th are P. Okay, from here to here D, and this bottom are F. Okay, so now one more thing here you can remember. In the Mendeleev classification, what I told you, he classified each group. If there is one, he told it is 1A, 1B he told, na? Okay, each group into subgroups. Okay, so this is 1A, this is 2A, S block as 1A, 2A, then P block as, this is 13th group is there, na? Consider it is 3A, 4A, 5A, 6A, 7A, then next this is 0th group. Okay, then next 13, we have 1A is over, next 1B starts where? It will starts here at the copper position. So it will be having, what is the electronic configuration? You can remember like that. What is the electronic configuration? 3D10, 4S1. So this is 1B, you remember. This is 1B, this is 2B. Like that 3B, 4B, like that we have. Okay. See, this set of elements, these 3 set of elements are considered as one group. Okay. Yeah. Next, again, lanthanides, actinides belongs to which group? I am asking. Here, 3rd group. See, this cerium, this follows this lanthanum element. Okay, so this thorium follows this actinum element. So it means this has to be, just imagine, this has to be placed here. Means how periodic table looks. Like the set of unequal, like symmetry lost here, right now. So this is a set of 14 elements will be lying here, means how you just imagine. Okay, so see, like lanthanides belongs to which group? 3rd group or 3B group. Remember 3B or 3. Okay.
Lanthanides and actinoids are radioactive?
Not all. Okay. Yeah. So next, what period they belongs to? 6th period lanthanides, 7th period actinides. Okay. Remember these 2 things. Yeah. Next. Now how many elements were known? 118. Okay. So now the elements with atomic number greater than 100, there is a standard set of rules to be followed for writing their nomenclature. For example, an element we have with 101, how you are going to write? Okay. So for 1 we should say an, for 0 you should say nil, for 2 you should say bi, 3 tri, 4 quad, 5 pent, 6 hex, 7 sept, 8 oct, 9 n. Okay, N. Okay, so now, so tell me, 101 means what I should say? Un. First letter should be capital. Un. Again nil. Un. Nil un. And the name of this should be end with IUM. Okay, Anil Aniyam. Okay, take the first letters in this case U, capital U, and the next N. For this letter it is N, again this is U. So UNU is a symbol for 101, element with atomic number 101. Is that clear? Okay, now tell me, for I have an element with atomic number 121. If I have, so tell me. Un by EM. So what is the symbol? UB U. That's it. Okay, like that. Okay, so now in the exam they are going to give you this side of UPSC name and this side official name. Okay, like this. Okay, they will ask you to match them. So Mendelevium, what is the atomic number? 101. So it should be Nil Aniyam. Okay, so Nobelium, Nilbium. Next Laurentium, 103. Trium. Next Rutherfordium, 104. Okay, Dubnium. Next 105. Next Seaborgium, that is 106. So like this. Yeah, these names comes from scientists or from some places. Okay, like Californium. Okay, like that. When we are studying about lanthanides and actinides, we'll discuss that. But now you just try to match them, remember their atomic number here. Okay, yeah. So just try to match this. See, we got this question in 2020 NEET. So tell me.
A1.
Anil Aniyam means what? Mendelevium. So A4. They are asking incorrect one. Okay. Next, Aniltrium means
Lawrencium.
103. Laurentium. Anilhexium means Seaborgium. That is 106. Okay, Darmstadium, and here it is saying as again 1, again 1, 111. Okay, 111. Okay, so this is the number they are saying, but Darmstadium has atomic number of 110. If you look here, it is have atomic number 110, but it is 111 given. Okay, so 111 is what? Wrong. So it means that is incorrect one. So which is incorrect? So where is our option? So this will be your answer. Okay, yeah. Next. Okay, try to remember. See, there is no time consuming thing here. Just if you remember, if you studied that in the book or in the class, then you can able to answer. That's it. Nothing to calculate, nothing to do right now. So try to stick to the NCERT or the class notes along with your NCERT book. Okay, next, how can you predict the block, period and group of an element? For example, I am giving you element calcium. So how can you predict its group?
Electronic configuration.
And its block. Okay, so we just, for predicting its block, just look at the last electron enters into which orbital. So calcium atomic number 20. So if you write its electronic configuration, you will be so argon 3 4s2. This is 18 over 18 electrons. 20 means 18 plus 2. Okay, so it means the last electron entering into s orbital. So I can say it is s block. Okay, and after this, so what they are saying? Block, period. So which period it is? What is the number here you are seeing? So fourth. Okay, period number also you can see the maximum principal quantum number says it's a period. So calcium maximum principal quantum number is how much? 4. So it is fourth period element. Okay, next group S block, number of valence electrons. So for saying group number, how many valence electrons we have? 2. So it is second group element. Okay, so for P block,
Number of valence electrons
Ah.
is 10.
why we are adding 10? That D elements are how many are there? 10 D block elements are there. So after that we have P block. So for every time if an element belongs to P block, so take valence electrons, add 10. For example, I am giving you carbon.
-2 increase.
Which group element it is?
2s2 2.
Write its electronic configuration first. Atomic number 6 means
1s2.
1s2, 2s2, that is helium 2. Next
6. 2p3.
2p2. So 2 plus 4, 6 over. So now how many valence electrons we have? 4. Okay, so 10 plus 4. So why? So how do you got that idea of adding 10? By looking at here. So which group it is? Like which block it is? P block, you know. So if it is P block, just add 10 to the valence electrons. So 10 plus 4, it is 14th group element. Carbon belongs to 14th group. Okay, like that. Next for D block, so take number of Ns electrons and number of N minus 1 D electrons. Okay, so for F block elements, all they belongs to which group?
3p.
3p. Fixed now, already we discussed. Okay, just I told you to imagine by keeping them. Okay, next. Now we need to discuss about properties of these elements. Okay, first one is what? Atomic radius. What are these properties? Means like
Physical.
physical properties and the chemical properties we have. Now, physical properties like their size.
Shape.
So size can comes from its
Radius.
radius. Okay, how this size or radius varies. If we go top to bottom of the periodic table in a group or left to right in the period, so what happens to its size or atomic radius? Okay, that is what we need to discuss here. Okay, so in the periodic table we have different elements. Now we have metals, non-metals and metalloids we have. Okay, so for metals we will be using metallic radius. To express their size, we will be using what in terms of metallic radius for metals. For noble gases, these noble gases won't react with any other species now. They are very stable. Therefore, their radius will be expressed in terms of van der Waal radius. What is that? Van der Waal radius. Okay. Now, why van der Waal radius? Noble gases will exist in their atomic form only now. Like helium gas if you take, like this only neon gas if you take, they will be, do not react with anything, they will be stays in atomic form. Now for other elements we have covalent radius. So we have three types of radius now. What is that? Metallic, van der Waal, covalent. Okay, so generally if we arrange them based on the increasing order, van der Waal radius will be greater one. Okay, so because van der Waal radius is measured between the atoms which are not combined but which are near to close to each other. Okay, metallic radius means just take two metal atoms which are rigid like side to each other, so distance between them. Covalent radius means that is formed by, covalent bond is formed by overlapping now. So see, these atoms are little overlapped. Now tell me which distance is smaller here? Covalent. So that's why radius is smaller here and van der Waal is higher. Okay, remember this order. Okay, next. So now how the atomic radii varies in the periodic table, like from top to bottom. Along the period we'll start first.
Atomic radii increases.
So variation down the group first. Okay, so down the group means lithium, sodium, potassium, rubidium, cesium if I take. So down the group what happens to the radius? Increased. If you see the values, you can observe here values are getting increased. These are experimental values. So why that those values are increasing, tell me?
Number of shells.
Huh?
Number of shells increase.
See, not only number of shells, that newly added electron is there now, that is going into the like next higher energy level, higher energy shell. For example, lithium, you tell me what is the atomic number? 3. So 3 means
1s2.
so if this is a nucleus, if this this is a nucleus, so we can write this is 1s shell and this is 2s shell. Okay, this is n equals to 1 and this is n equals to 2. Okay, similarly if I go further, what is the atomic number of sodium? 11 right now. So it means that electrons will be goes to the higher energy level, something like this. So now for lithium, 3 electrons only, so 1s2 over, so 3s1. So lithium valence electron is here. For sodium, it will be here. So now look, atomic radius means distance from the center, to the valency electron. So this is the distance from the center to valence electron of lithium, and this is the distance for, this is the radius of what? Sodium atom, and this will be for potassium. So as we go down the group, what happens to their radius? Increased. So down the group radius increases. So you can get a graph if you observe something like this. Okay, this is for alkali metals, this is for halogens. Okay, got the clarity here? Next, these are the experimental values. So what is the reason you should say? So down the group atomic number increases, therefore number of electrons increases, but that newly incoming electrons will be added to the higher energy shell. Therefore electron cloud is increased. So the like distance between the nucleus to that valence electron cloud will be more. That's it. Okay, this is about what? Down the group. Okay, now we will discuss about period. Okay, so variation of atomic radii in the along the period. Okay, so now what happens? Take some elements for our observation. So tell me what elements will take? Beryllium, boron, carbon, let us take, nitrogen, like this will take. Okay, so now tell me what is the electronic configuration? Atomic number 4, 5, 6 here, 7 here. Tell me. 1s2, 2s2. This one 2s2, 2p1, and this is 2s2, 2. This one 2s2, 2p3. So see here, in the previous case, this n value got increased. This initial coefficient number is increased. Now you are, if this is a nucleus, this n value got increased the previous case, like new electron enter into like this, so I have mentioned like this. But in this case, if you see, atomic numbers are increasing, number of electrons are also increasing, but that increased electron is also entering into the same shell number right now. So same shell here, n equals to 2 only now. So it means what happens to its radius?
Same.
It means shell number will be same, but number of protons are increasing now. It means nuclear force is increasing. So positive charge is increasing in the in the nucleus. It means what it will do? It will strongly bind the electrons and attracts close to towards the nucleus. So what happens to the size? Size decreases. So atomic radius decreases, I am saying. So across the period, what happens to the size? Our atomic radius decreases. Okay, like this you can understand. Okay, so see, atomic number also, see, in general the covalent and van der Waals radii decreases with the increasing atomic number as we move from left to right, from left to S block to P block. Okay, this is about the across the period. Next. So look at this experimental data. So lithium to beryllium like this, if you see, what you are seeing size 152, 111, 88, 77, 74. So size values are decreasing. See, if you observe, they haven't included noble gas. They stopped it up to halogens only. So what I told you, noble gas atomic radius is measured in terms of van der Waal radius. So van der Waal radius is greater than this covalent radius and metallic radius. So always noble gases will be having larger size exceptionally when we compare with the other elements. Okay, that's why that is not in comparison here.
They also have maximum electron repulsion.
That's what expanded cloud we will be seeing there. Okay, yeah. Is that clear? So down the groups, down across the period, what happens to the size?
Decreasing.
See, as atomic number increasing in a period, size got decreased like this. Okay, next. Next, we have discussed about atomic radius. Now it is for ionic radius. Ionic means if I have an atom A, if I have an atom A, I can say its radius are atomic radius. Now what are the respective ions we can get from here? See, if I add one electron to this, it becomes A minus. If I remove one electron, it becomes A plus. So cation, anion of this atom A. Okay. So now if I ask the size order for these three species, what is the order, you tell me?
Order A minus A plus.
Minus A plus. Always cation will be smaller for a respective element when we compare with its anion. Why? Because electron clouds, electron number of electrons is more, so electron cloud is expanded in this case, therefore its size will be larger. Here positive charge is more than the negative charge, therefore positive charge means nucleus charge is more, it will strongly attract the electron cloud, so size becomes smaller. Okay. So now we need to study here isoelectronic species. It means what? Iso, same electron, same number of electron containing species. So for example, I am fixing the number as 10. So tell me the ions or atoms having 10 electrons.
Neon.
So tell me elements having like atoms or ions having having 10 electrons. See, I am taking sodium ion. How many electrons are there? 10. And the next fluoride ion I am taking. How many electrons are there? 10. I am taking Mg2 plus. How many are there? 10. And I am taking here O minus 2. How many are there?
N3
minus 3. Tell me how many electrons? 10. All of them are having same. So ions, all of them are ions and isoelectronic species. So 10 electrons and these are isoelectronic species. Okay. So now arrange them based on their atomic radius or ionic radius. So how do you arrange their ionic radius order?
Mg2 plus.
So what I told you, if a species having same number of electrons, in that case what we need to look, the nuclear charge. So size is inversely proportional to nuclear charge. Nuclear charge means what? More positive charge. If it has more positive charge, size will be less. So which is smaller size here? Mg2 plus will be more positive charge, more nuclear charge, lower the size. Okay. So this will be smaller, then next like this and like this. More negative charge, more is the electron cloud expansion, so size will be bigger. Okay, like this. Is that clear? Okay. So now yeah, tell me in this case
Si2 minus is larger than.
which group What is the atomic number for chlorine? 17. 1 electron added. So 18 electron here. Sulfur atomic number is 16. So minus 2 means 2 electron added here. Here also 18. Both are same electrons. Isoelectronic species. Now tell me. S
minus is larger.
Sulfide ion is larger size than chloride ion. Okay. So write these things. We'll discuss further. Okay. Let's solve few questions. Answer this.
Decreasing order of atomic radii.
Correct decreasing order of atomic radii.
Li, B, B, C.
How that elements like arranged? They belongs to what? Period or group?
Period.
Same period elements. So now how can you arrange? Lithium, beryllium, boron, carbon. So what happens? So if you go like this from left to right, size decreases. So larger one is like this. So where do we have?
Second one.
That's it. Okay. Next, last year's question it is. Next,
Following option represents the correct
you should answer this.
of Armstrong and Young respectively.
Third one. Okay, we'll see. How easy it is? So tell me first of all which is larger size here? N minus 3, O minus 2 and F minus. This is the order right now. So larger size means it should have bigger value. So N minus corresponds to bigger value here and here. After that O minus 2, so here we have. Okay, so third one. Easy only. Okay, next. Next term is ionization energy. So what do we mean by ionization energy? Tell me.
Removal of electron from a removal of electron from a neutral isolated gaseous atom.
See, the energy, if this is an atom having one valency electron, now the amount of energy required to remove this valency electron from the atom is called
Ionization energy.
so ionization energy. The minimum amount of energy required to remove an electron from outermost orbit of an isolated atom which is in its gaseous state, okay, known as ionization energy. Okay, we should remove the electron from the element that should be
In gaseous.
isolated one and it should be in gaseous state. Generally some elements will be in the solid or liquid state. We should not take from there. So first convert that into respect to gaseous form. Okay, then you remove electron from here. This energy, if you remove electron from this gaseous species, it will become like this now. So this is called its ionization energy. If you do from here to here, you should not say it as ionization energy. Okay, so this process includes what? Conversion of solid to gas means what is this process? Sublimation, right? This is energy sublimation. So this includes sublimation energy plus ionization energy. Okay, we are not talking about this one. We are talking only about this. So if we remove one electron, that will be first ionization energy. If I remove electron from here, from unipositive ion, you should say second ionization energy, IU2. Again from here, like that. Those are successive ionization energy. Always just tell me, removal of electron from atom is easier or its cation form is easy?
Removal L.
from its atom is easy because in its cationic form it is having more positive charge than the electron charge right now. So it means positive charge strongly holds the valency electron, therefore it requires more amount of energy. So always removal of electron is from atom is easier than respective cations right now. So now tell me what successive ionization energies always will be like this: IE1 greater than IE2, that will be greater than IE3. That's why I have mentioned it like this. Okay, clear? Any doubts are there? Any confusions anywhere? No. So now what we need to study, how this ionization energy varies.
Sir, you gave opposite.
No, sorry, here, okay, sorry. So what I should write? IE, successive ionization energy should be greater, na? So IE3 greater than IE2 greater than IE1. Okay, this is the perfect one. Okay, clear now what I am explaining here? Yeah. So now how this ionization energy changes down the group or across the period, that is what variation of ionization energy. Okay, yeah. So let me check. So tell me across the along the group, first tell me what happens. You tell me electron. See, if this is an atom having nucleus, this is the nucleus of an atom and this is the electron clouds of atom. So tell me, if I have electron here which is very near to the nucleus, I am talking across the group, I mean down the group I am talking, and I have another element having valence electron here. So which will be hold strongly to the nucleus? Tell me. The one which is having smaller size right now. So down the group what happens to the size?
Size
Increases. So it means removal of electron is easier from the larger size one. Okay, and it is difficult from smaller size. So smaller size is at the top, larger size is at down. So down the group ionization energy down the group ionization energy decreases. Why it is decreases? Due to large size it requires less amount of energy to pick out the valency electron. Okay, yeah. So what I can say, the force of attraction decreases as size increases down the group, therefore valency electron can be easily removed from the bottom element. So down the group as we go down the group, IE value decreases, ionization energy decreases down the group. What happened? Okay, down the group over. Now across the period you tell me
decreases.
value of ionization energy. What happens? From left to right. What happens? Increases. Why increases?
Effective nuclear charge increase.
Why increases?
Atomic radius is
Decreases. Okay, atomic radius decreases. Why? Because the nuclear charge will be more across the period. So due to decrease in size or due to increase in its nuclear force on the valency electron, the amount of energy required to remove the electron will be more. Therefore ionization energy increases. So generally what I can say, generally ionization energy IE increases from left to right. Okay, and there are some exceptions here. So when we will be seeing that exceptions is when we have half filled and fully filled electronic configuration. So one of the factor that is affecting an ionization energy is what? electronic configuration, that is half filled and fully filled electronic configuration. See, half filled and fully filled electronic configurations are containing species are highly stable right now. So removal of electron from that species will be difficult. Okay, so therefore their ionization energies will be greater when we compare with the neighboring or the adjacent atoms. For example, we will say lithium. Tell me group period elements here. Beryllium, boron, carbon, nitrogen, oxygen, and last is fluorine here. Okay, neon here. Okay, we will take like this. Where do we got? Okay, oxygen is removed here. Okay, oxygen, fluorine and neon. So now tell me, where do we have fully filled electronic configuration? Neon. So we know neon is having full filled configuration, so definitely it will be having highest ionization energy. Right now, after this, if I compare fluorine and oxygen, tell me, fluorine electronic configuration is 2s2, 2p5. This is 2s2, 2p4. This one 2s2, 2p3. So this is half filled, na? P orbital is half filled. Okay, like 3 orbitals will be there for p orbital, p subshell having 1 electron each, so half filled. This is 2s2, 2p2. This is 2s2, 2p1. Here 2s2 only. This is 2s1. Now look here. So you are seeing for fluorine chlorine case, both of them having normal unpaired electron is there, but electronegativity of fluorine is there, therefore that makes it to be having more ionization energy than this oxygen. Okay, up to here it is clear. But if you compare nitrogen and oxygen, nitrogen is having half filled configuration. Due to that reason it is more stable, so more amount of energy is required. So I should insert here nitrogen first, then oxygen. Okay, after that between nitrogen and carbon, nitrogen only. Between oxygen and carbon, oxygen only. Okay, between boron and carbon, see it is having 2 electrons, it is only 1 electron. If we remove that 1 electron, it has fully filled s orbital, so it means it requires less energy than carbon. So carbon here. Next, boron and beryllium, if you observe this, if I remove this 1 electron, it will be having 2s2. Okay, here we have electron in the s orbital, that is fully filled. Okay, but you should say s orbital is more closer to the nucleus when we compare with the p orbital. So it means if nucleus, the s orbital is close to the nucleus, means that electrons are strongly binded to the nucleus, s orbital electrons, when we compare with the p. See, if they strongly binded, is it able to remove electron easily? No. So which is easy to remove? P orbital electron from boron. So that's why we can remove electron for boron easily than the beryllium. So we can say ionization energy of beryllium is greater than boron. And between lithium and boron, lithium will be least because only 1 electron is there. Na? So but if I remove this electron, it will be getting helium gas configuration. Na? So like that. Is that clear? So what are the exceptions here you have seen? Boron and beryllium. So what is the name of that concept? That is called as penetrating capacity, PC. It means the s electrons of beryllium are very close to the nucleus, therefore required the amount of energy required to remove that electron will be high when we compare with the p orbital. Okay, yeah. Penetrating capacity of s orbital electrons are more here. Okay, next write that, and remaining things, remaining applications of ionization energy and electron affinity we will study in the upcoming class. Okay, any doubts are there in today's discussion? If no doubts, we will wind up the class with 1 or 2 questions here. Yeah, this one last question, remaining we will discuss in the upcoming session. So let me take one easy question. Yeah, this is easier than that. Okay, so tell me, answer this thing. Look at their electronic configuration, just now we discussed. Now arrange their energies. Which will require higher energy, tell me?
1s to 2s2
1s to 2s2.
and 1s to 2p3.
That is fine. That complete order you remember. First, second period elements order I told now. Okay. Highest is for fluorine,
Third option.
neon. There is no neon gas configuration. There is no fluorine gas configuration. After that we have nitrogen and oxygen. Okay, but nitrogen electronic configuration is there. This one. So that corresponds to 4, highest one. After that oxygen. Do we have oxygen electronic configuration? Yes. Look at here. 1s to 2s to 2p4, 8. So that will be the next one. Next, after this what we have? Carbon. After that beryllium. Next boron, like this. So now here this is for boron, this is for beryllium. So tell me, now arrange them. Least is for boron, so least value is here, and this is for beryllium. Now which option?
4.
Option 4, A2, B3, C, C4, D1. So option 4 is your answer for this question. Hope this is clear. Now if you want, you can open our modules, just try some questions. You can definitely able to solve questions from these things which we discussed today. Okay, if no doubts we can wind up. If you want, you can just give a try for these questions at the end. Yeah. So those who are watching in online, so just answer me for these 2 questions in the comment box. If there is any error in your answers, I will be correcting them. So thank you for watching. Stay connected with this channel. Thank you.